All right, so in the first chapter we talked about biomechanical levers and how the body is basically a biological system of pulleys and levers in order to produce motion. So now we're going to go a little bit more into functional lever analysis. So we want to know how lever problems apply to functional movements that people are doing. And we will be going through a lot of these in lab for pretty much every part of the body. And so I kind of wanted to give you a model for looking at these type of questions. So when we do functional lever analyses, we are going to analyze any motion, as a lever system. And there's a series of questions that we will answer every time we do it. So whether we're analyzing standing shoulder flexion, or side-lying shoulder abduction, or side-lying hip abduction, or any other motion that you could possibly imagine in the body, we're going to ask these questions. So first of all, which joint is being analyzed? Sometimes it's obvious, like for shoulder flexion, it's the shoulder. What's the primary motion happening at the selected joint? Well, again, for shoulder flexion, it's flexion. And if we're, raising the hand up, when we're lowering it down, it's shoulder extension. Which primary plane does the motion occur? Is it the frontal plane? Is it the sagittal plane? What is the axis of the motion? Is the movement with or against gravity? Is gravity or muscle the force producing the movement? So we'll talk about that. Is gravity or muscle the resistance to the movement? Well, obviously they're going to be opposite. If gravity is the force, then muscle is going to be the resistance. And if muscle is the force, then gravity is going to be the resistance. So is the muscle acting to overcome or slow down gravity? It's going to be one or the other. Unless you're in a gravity reduced plane, we'll talk about that as well. But the muscle is usually acting to either overcome or slow down gravity. Which major muscle group is the agonist, is the prime mover, and which is the antagonist? And is the agonist performing a concentric or eccentric contraction? And then is it an open or closed chain activity? So we're going to do a sample analysis with a little case study, and we'll go through all of these questions. So in our sample analysis, and this is one of the pre-lab worksheets you have for the first lab. It's the analysis, the first part of the analysis in this one. So after being hit on the left lateral pelvis by another player's helmet in a football game 6 weeks ago, the middle linebacker is experiencing weakness in his left hip abductors. So he's been performing the strengthening program prescribed by his PT in supine. So in supine, for hip abduction, it is a reduced gravity position. So he's weak because of his injury, and we had him in a reduced gravity position. But now he's increased the strength of his hip abductors enough to be progressed to performing hip abductor strengthening in right side lying. So it's his left hip. We're side lying on the right. We're going against gravity. So it's a more difficult motion. So one of the things that we're looking at a lot of times with exercises is sometimes how can we make this exercise easier, and sometimes how can we make this exercise harder. So when you think about the effects of gravity and how it's acting on the limb, obviously when you're working with a healthy person, you're usually trying to make the exercise harder. But sometimes when you're working with someone with a neurological or an orthopedic injury, you have to figure out how you're going to make it easier. How are you going to still strengthen this muscle even though the person doesn't have anti-gravity strength? So this is a way of thinking about it, is you can change the lever, you can change gravity, you can change their relationship to gravity to make it easier or to make it doable. So with our football player, he's got anti-gravity strength now, and we're going to analyze the motion of lifting the left leg toward the ceiling inside lying. Okay, so here's our picture of that motion, and the joint being analyzed is the hip. In some of the functional analyses that we do, we're going to be doing multi-joint motions like a sit to stand. That's a really good example of a functional motion. We are not going to analyze multiple joints at once. We're going to pick one and we're going to analyze that one. So let's specify. But in this one, we're analyzing the hip. The primary motion happening at the hip is hip abduction. Okay? So, hip abduction occurs in the frontal plane around the anterior-posterior axis. Okay? Gravity is the movement with or against gravity. So when we're lifting the leg up, the movement is against gravity. And muscle is the force producing the movement. And gravity is the resistance to the movement. The muscle is acting to overcome the resistance of gravity. Okay, so that might seem obvious, but then we'll discuss the implications of that. So when muscle is the force and gravity is the resistance, we have a third-class lever. So when you look at the hip, the axis is the hip. The force is being applied at the greater trochanter, because that's where the hip abductors insert. And the resistance is the entire weight of the leg with gravity acting on it. So the force is between the resistance and the axis, and that makes it a third-class lever. Okay? And then the muscle is acting to overcome gravity. So is it an eccentric or concentric contraction? When we're lifting the leg up, the hip abductors are shortening. It is a concentric contraction. And concentric contractions are always working to overcome gravity. They're always going against gravity. So that is one of the ways that we can define whether it's eccentric or concentric. We always know where gravity is. If you're not sure, just drop something. And if you're going against gravity, it's a concentric contraction. And so then you can figure out which muscles are shortening at that point if you're not sure. So which major muscle group is the agonist and which is the antagonist? So we know the hip abductors are shortening to overcome gravity. So the hip abductors are the agonist and the hip adductors are the antagonist, the opposite group. Is it open chain or closed chain? Well, we know the proximal segment is relatively fixed, lying on its side, and the distal segment is not, and so it is an open chain movement. So we can go through that same analysis. I'm going to go back to the beginning of this. Phase 2 on the worksheet is to analyze the motion of lowering the left leg from the raised position. So it's still the hip being analyzed. The primary motion happening is hip adduction. The hip is returning to anatomical position. Okay, it's still in the frontal plane with the anterior-posterior axis. That doesn't change. This time it's going with gravity. So gravity is producing the movement and muscle is resisting it. And the muscle is acting to slow down gravity. So we know that when muscle's acting to overcome gravity, it is a concentric contraction. When the muscle is acting to slow down gravity, it is an eccentric contraction. So when it's working to overcome gravity, it's a concentric contraction. When it's working to slow down gravity, it's an eccentric contraction. So which muscles are working to slow down that adduction of the hip? Which ones are lengthening? The hip abductors are lengthening. So the gluteus medius and gluteus minimus are lengthening to slow down the pull of gravity. So the hip abductors are still the agonist, even though we're doing the opposite motion. And the hip adductors are still the antagonist. So the hip adductors aren't pulling the leg down. They are just along for the ride. The hip abductors are resisting the pull of gravity, since gravity is the force. So now that the axis is still at the hip, the resistance is at the greater trochanter, And the force is the gravity acting on the whole weight of the leg. So now we've switched to our second class lever. So the eccentric muscle contraction is a second class lever. It's still an open chain activity. So to sum this all up, we're going to look at eccentric versus concentric contractions. So with regard to gravity, eccentric contractions are always slowing down gravity. They're going with gravity, in the direction of gravity. Concentric contractions are overcoming gravity. They're going against gravity. Eccentric, the muscle, the agonist muscle is always lengthening to put the brakes on, slow down the pull of gravity. Concentric contraction, the agonist muscle is always shortening. With an eccentric contraction, the muscle group is going to be the group opposite the direction of motion. So when we were lowering the leg, we're doing adduction, and the muscle group is the abductors. With the concentric contraction, the muscle group is always going to be in the same direction of the motion. The antagonist with an eccentric contraction is the muscle group in the same direction as the motion. And the concentric, the muscle group in the opposite direction of the motion. So just the opposite from the agonist. With an eccentric contraction, gravity is always going to be the force, and muscle is going to be the resistance. The concentric contraction, muscle is going to be the force, and gravity is going to be the resistance. So after listening to this, download that lever worksheet and work through some of those lever problems. And then in lab, Lisa and Claudia are going to go through those lever problems with you. And in fact, we're going to go through them in every lab. We're going to do these types of lever problems for every different joint, so you get the idea. And really the whole point of it is, in the category of why do we need to know this, is so we can effectively perform therapeutic exercise interventions that are appropriate for our patients' level of, to challenge them appropriately for their level of ability. So this really, it's kind of an interesting area, and it's something that comes up all the time.